Well, Ben and Joe, thank you so much for joining me. And thanks to all of you for sticking it out. I know we're getting near to the end of a long week. And so as we get started, I would love to, Joe, start with just kind of a level set. Where are we at with quantum computing? What is real right now and what is still hype?
Sure. So I think it's actually a really interesting time for quantum computing at the moment. So if you look at what's going on in the space, quantum computers are starting to reach a point where they're passing the number of qubits in them is passing the number of transistors in, say, or the number of bits in an Atari 2600. So it's still super early, and the systems are still unreliable. So we're working towards error correction. We're starting to see the first error correction experimental demonstrations that happened last year. So it's getting to an inflection point, but it's not really at the point where it's solving hard problems for users. So it's still early, but it's really picking up momentum at the current time.
And so does that, you talked about a couple of things there. You talked about error correction. There's still a lot of barriers, but you can see some of those practical use cases. You can see some of the, or maybe not practical, but you can see some of those use cases. Are we at the point where you feel like we see line of sight to overcoming some of those, and what does the timeline look like right now?
Yeah, I think that's a good question, and actually, I think sometimes the best answer on this is not to give my own numbers, but instead to point to a report. There's a report written each year for the Global Risk Institute, and what they're trying to do is figure out how long is it going to be before we have quantum computers that can break encryption, specifically that can break RSA 2048, which is, in some sense, one of the threats of quantum computing that we're talking about. But they also ask, basically they survey about 50 different experts. They ask them to estimate the timeline, like how confident are you will see such a quantum computer in 1 year, in 3 years, in 5 years, and so on. And for that threat line for quantum computing, it's kind of 10 years, 12 years, something like that. But they also ask about commercial applications. And if you look at the responses there, you see the kind of median of the expert opinion switches from thinking it's less likely than not to more likely than not in the 3 to 5 year window, which, well, that's last year's report, so subtract a year, say 2 to 4 years, and I think that's fairly realistic. But there is uncertainty around this.
Great. So Ben, Joe talked about risk, and I want to just definitely get to that in a minute, but I'm curious, when you look at sort of the spectrum between risk and reward right now, and you look at where quantum computing is today, where do you see us on that spectrum today?
I think, look, importantly, everyone has recognized that quantum computers happen to be particularly good at the maths that sits behind the encryption we rely on. And so that's a well-accepted problem, and we have standards starting to emerge. We have the algorithmic standards that were published last year, and now industry is working to flow those down through protocols, industry-specific standards, and global vertical standards. So that's happening. I think the timeline of the quantum computer becoming powerful enough to break cryptography and the migration time are starting to diverge. NIST has announced that RSA and ECC will be deprecated from 2030 and completely disallowed from 2035. To some extent, there's a regulatory timeline that has already emerged that is separate from when we have a cryptographically relevant quantum computer. So I think that's useful in narrowing down the problems that people are trying to solve and when they're trying to solve them by. And so to some extent, I think we are fairly balanced as it stands today.
So I want to spend our time, I definitely want to talk about those risks. I want to talk about then some of the upside, because I think the thing that's helpful for developers is to figure out two things. What should I be doing now to be preparing for the future? And then why are we preparing for, what does that future look like? So why should we as developers investing in them? So let's start by talking about the risks, right? You mentioned cryptography. I've started to see, for example, Apple talked about preparing iMessage for post-quantum cryptography. So we do start to see that even in mainstream, right, companies. But talk to us about what the worst case scenario risk is for quantum computing at this point. And then we can work our way back to what's the most realistic ones.
Yeah, sure. So as you rightly say, industry's already moving. You have platforms like Cloudflare, which is securing our internet infrastructure, if you like. I think they reported just a couple of weeks ago that about 50% of the human-generated traffic now is already being using post-quantum cryptography through the Cloudflare platform. So that's a great start. AWS are rolling it out. Signal Messenger have rolled it out. Apple have rolled it out. Others are doing it. So I think one of the fundamental areas we need to focus on is that core infrastructure. So there are still work going on IETF and ETSI standards for things like certificates, for DNS, and those fundamental technologies on which we build our applications and services upon. So it's going to take a little while for that to happen over the coming 2, 3, 4 years. But in the meantime, the supply chain is beginning to move now. So you will find from next year onwards, Cisco's, Palo Alto's, etc., shipping devices that are quantum safe. And so we can start to build the layers up here of protection against this problem.
So at least in my view, the worst case scenario is really bad. Actually, maybe more bad than has been highlighted here, which is that actually, if you have a large-scale quantum computer and you decide you want to use it maliciously, the worst thing you can do isn't to read people's emails or to compromise their bank account or something like that. The worst thing you can do is to compromise DNS. So you forge a root certificate, like you just start signing yourself with a root certificate. And so that's one key you have to break. And then you break the Microsoft key that they're signing Windows Update with, and that's enough. Then you can compromise every Windows computer plugged into the internet by just pretending to be Microsoft and pushing a malicious update. So the bad case is really, really bad. And it might be slightly worse, again, in the sense that we're talking about post-quantum cryptography, which is an attempt to come up with new crypto systems that are not vulnerable to quantum attack. But we don't understand quantum algorithms all that well yet. We only have a relatively small number of examples. And so the level of confidence we have that any particular crypto system is actually secure against quantum attack is pretty limited. The number of people that are trying to come up with quantum attacks on these new crypto systems is really small. It's like dozens at most. So there's a real risk there.
Yeah, and I think that's a really good point, because I think what the this quantum problem represents is a bit like AI in a way, that the pace of change that we're going through here, we've relied on RSA and ECC for like decades, okay? And there's lots of hard-coded stuff sitting in applications all over the place because everyone's like, it's fine, it's okay. Whereas now I think we're saying, actually the future is going to be about change. That cryptographic algorithm we think is secure today may not be secure in 10 years' time. I don't think we're going to have another 40 years of one algorithm being secure, for example. So developers and people building products and services need to actually think about the security requirements as a fundamental feature of their product or service, and the ability to continually update and modify that as a baseline, right? It's a non-negotiable. It's often referred to as crypto agility. It's not a term I love particularly because it gets misinterpreted, but fundamentally assume that the cryptography you're using today may not be safe in 3, 4, 5, 10, 20 years. We don't know, is the point. I agree with Joe there.
I mean, this is a good point about crypto agility. It's extremely important because if you look at the standardization process that has been happening at NIST, some of the candidate protocols have been broken just during the couple of years that process has been running. And some of these are classical attacks, not necessarily quantum attacks. So with any crypto system you adopt, there's always some risk that it will need to be deprecated, and you don't know what the timeline for that is going to be. There is an even bigger potential risk, which is that perhaps the kinds of problems that we know about that we can base cryptography on are all easy for quantum computers. We're not 100% confident they're not yet. So there's always that, whatever the worst case scenario is, there's always like one scenario that's a little bit worse. And I don't want to put everyone off quantum computing because I think it's definitely worth the transition.
Agreed.
You see, and so on. But
I think what gives me some confidence, just if I may, is that actually the global community has been working on this together. So the NIST process was actually a really good process. We had candidate algorithms from all over the world. They've been thoroughly tested. There's continual research and publication and work going on in that field. And that is continuing. So having algorithm standards is just one piece of a jigsaw puzzle. Yeah. Moving that down into how that works its way into protocols, how that works its way into, certificates, DNS, etc., is work that community is plowing through right now. So I'm encouraged by the focus that it's getting and the amount of horsepower, if you like, that's going into these problems, because everybody recognizes those worst case scenarios.
Yeah, and Joe, you said something that I want to make sure that we all heard, because you talked about the worst case scenario isn't necessarily the one that those of us on the outside assume is, which is collect all the data now and decrypt it later. You mentioned the Windows update, and we all know what that looks like 18 months ago, right? With CrowdStrike, you try to get on a plane when all the screens are blue. We've lived through that, and that wasn't malicious. That was just a bug in a piece of software, right? Imagine if someone was actually doing that on purpose and on an even broader scale, right?
But that's not the worst case. The worst case is you don't know they're in the system. Right?
So you don't see the blue screen of death. You see something else, and it's
and anything can be compromised at any time. That really adds a layer of challenge on top of this, coupled with this risk of we don't actually know for sure that post-quantum cryptography will mitigate the risk of quantum computers. And I know you mentioned the research that's been done on a worldwide effort and so on. But if you look at the number of people that have had any success in constructing algorithms that run on quantum computers with an advantage, it is less than 250 people worldwide that have done this more than once. Sure. And not all of those are working on PQC. Maybe, 10% of them are working on PQC? So it's the number of experts that are actually trying quantum attacks on these is relatively small. And how that changes as quantum computing evolves and blooms, and instead of 250 people, you have 250,000 people. I think that's very hard to predict.
Yeah, and we've been doing things like side channel protection of PQC in hardware, and the same applies, right? The number of people trying to do those side channel attacks on that piece of hardware is tiny. The attack surface area is tiny, and it is only going to expand. So the way in which we implement the cryptography is categorically important. So we've designed things like, in software, hardware co-design, so that actually the parameters for those countermeasures can be continually updated over time, eating into a piece of baked silicon. That is fundamentally important to making sure that these algorithms and implementations stay secure over time, or can be updated as much as we can possibly predict at this moment in time.
Yeah, so it sounds like we've talked about the worst case scenario, and the worst case scenario is very bad. And it does seem like the question is similar to the conversation that developers are having when they talk about AI, which is simply, we know there's some upside here. We don't actually know what it is because we haven't gotten to that point yet. We also know that there's some huge risk in an AI. That's because it is non-deterministic, so we just don't know where it will wander off and what it will do. The question I have is, if the risks are so great with quantum computing, why? Why would we do this? What is the benefits? What are the upsides?
So, the obvious upside of quantum computing is that it is better computers. That's the promise of quantum computing. Today's quantum computers aren't really better computers, they're kind of worse computers, but we're on the way to them becoming better computers.
In what way? Just clarify. Yeah.
So they're computers with an extra trick. So they have this ability to take advantage of a quantum effect during the processing of information that exploits what's called quantum interference, where you're exploring multiple possible branches of a computation and you're able to extract information about some combination of those branches. And if you use it in just the right way, you can use it to get really large acceleration. So like an example of a problem that we've seen a big acceleration on, something I worked on right before I started Horizon, was on something called Gaussian process regression, which is a machine learning model. And it turns out for a GPU regression, if you go from 1,000 training points to 1,000,000 training points, the slowdown for a conventional computer is about a factor of 1 billion. If you do the same thing on a quantum computer, the slowdown is a factor of 4. And if you were to go from 1,000,000 training points to 1 trillion training points, it would again only be a factor of 4 slowdown. So the potential to drastically change what is computationally accessible to allow us to tackle problems that were never before possible is really enormous with quantum computing. And what I would say is it's the one model of computation, it's the one change to computing that we have seen since the very first computers emerged that fundamentally changes what computation means, that fundamentally changes what is accessible. And if you look at the growth of the world, of the GDP of the world over the last 150 years, if you go into our world and data and plot it out, what you see is that there is a kink in the curve. It's growing exponentially at one rate. And then, 1950, there's a kink, and it grows at twice the rate from then until now, more or less, with minor peaks and troughs averaged out. And it just so happens that that is about the year the first commercial computer was sold. Mm-hmm. And you could say, well, no, this is, like post-World War II growth and so on. And of course, that's part of it. But could you imagine the world economy today without computers? If we had to go back and just eliminated all the computers in the world? It's kind of hard to imagine what that world would look like, but it wouldn't look like the world we live in. So the potential of quantum computers is to be that same step change again. And one of the things about quantum computing and quantum information processing more generally is that you start to get new forms of cryptography as well. So you see things like quantum key distribution that provide a limited amount of the capabilities that public key currently allows for, but it's information theoretically secure. It doesn't matter how big a quantum computer your adversary has. There's just not enough information in the messages exchanged to figure out the key. So there are new possibilities that are opened up, both in terms of security and in terms of just a really wide range of applications where we potentially stand to benefit from quantum computing. But the price we have to pay with this is that we're going to have to move away from RSA, we're going to have to move away from Diffie-Hellman, from the existing crypto systems. But maybe that's a good thing because maybe they're not that secure anyway. Quantum computing is a way of breaking them, but...
Yeah, no, absolutely. As I say, I think it represents this change into the way in which we approach security. First and foremost, security should not be an afterthought. Security, given the amount of compute that's out there, classical or quantum, and whatever else comes next, the data that we are relying on a day-to-day basis has a value, has disruptive capability, and needs to be secured. So all developers, all products and service people need to be thinking about that and adapting as we learn more. As Joe says, there's a huge amount we haven't learned yet about it. And even just the growth of AI today is already driving more security at the edge of the network because those edge devices are hoovering up data points and creating data. And if they're open, then someone else's LLM is going to go hoover that data up and use it. So that data now has value, right? So for the company you work for, the business you work for, having security as an inherent part of your product is really important because you need to protect your boundaries and your customers' boundaries of your data, etc. So I think if nothing else, if the quantum threat as we perceive it today drives better security posture full stop, then I think we'll be on a really good place.
Yeah, so in the time we have left, I would love to hear, since we are in a room full of developers, presumably, give us the 90-second, each of you, what are the few things, I know this is a much longer question than 90 seconds, but you get 90 seconds each. What are the things that developers should be doing today? Give them like one or two things to be preparing for that future on both sides, for the upside and to prepare for the risks. Joe, we'll start with you.
Sure, so from our perspective, we're a dev tools company in some sense. We build quantum programming languages, we build the compilers and the execution stack to execute them on hardware. So certainly I would encourage any developers out there to play around with quantum computing to have some exposure to it now. But what we're building towards is to try to automatically accelerate classical code, code written for conventional computers. So to take code that's written in C++ or Rust or whatever it happens to be, and accelerate that, automatically construct the quantum algorithm so that you do not have to become an expert in quantum computing and run that on hardware. Now, I think, if you're thinking about where does quantum computing come in for you, what are the opportunities, it's going to be a couple of years before it's really used in production, before it's really solving hard problems. But the problems that are most amenable to it, that are most worth thinking about, are things that have small input and small output, but require a lot of processing. So often people talk about optimization problems, but there's a lot of other problems that fit into that category. So that's what I'd encourage you to look at.
Yeah, and as I kind of alluded to earlier, I think developers just need to approach security as part of the thinking of their product, and then start thinking about the flexibility. So by coding to APIs, so let's take an OpenSSL API, for example, nice and accessible to everybody. It's a really solid API, and if you code to that API, you can change the cryptographic library sitting underneath that API with relative ease, okay? If you're not doing that already, start doing that, right? Because that's a great step to giving that agility within your code or your application. And then you can choose an open source library, you can choose a commercial library, and you can plug that in underneath there to give you that agility. So I think real pragmatic steps taken there. And I think also for enterprises in general, we are being encouraged currently to go out and do algorithmic discovery of where all this cryptography is in your network. And whilst that's a noble gesture, for most enterprises, they wouldn't know one end of a cryptographic algorithm from another. And therefore, actually, you're asking them to go boil an ocean. What I would suggest is that 70, 80% of the cryptography that you use on a day-to-day basis in any enterprise is sitting within your supply chain. So go engage with your supply chain. Go talk to your Cisco's, your Palo Altos, your Amazons, and that developer, crucially, who built that thing for you 10 years ago, and you have a 15-year maintenance contract with them to maintain it. That's a thing you're probably going to have to pick up, look at, touch, change, re-architect, do something with, and it's going to take you time. Yeah? So the supply chain is a really interesting way to go and see what your posture looks like relatively quickly. Then you can get into the discovery piece of the algorithm in an area you've identified first. So rifle shooting is quite a good way to look at it.
I'd strongly agree with what Ben has said, in the sense that the threat I talked about earlier, compromising DNS, compromising Windows Update, these aren't a thing that a bank or any particular organization can solve on its own, except maybe Microsoft, but the situation is really such that it needs to be a community approach. You need to know where you're vulnerable in your supply chain, and you need to kind of mitigate that. So it really requires a community effort. It requires everyone working together to mitigate the threats.
Great. Well, Ben and Joe, thank you so much for your time, and thank you to all of you who stuck with us and stuck it out through Web Summit. Let's give them some appreciation. Thank you, guys.